Thank you. It's great to be here at my first in-person thing since COVID. Thank you to Omri, Mike, and Tony for organizing. Okay, so for today I'm going to be talking about two things: the online list labeling problem and history independence. This is based on a paper that's with Michael Bender, Alex Conway, Martin Farich-Colton, Hannah Komlosh, and Bill Kuzmal. I know at least some people here have seen some version of a talk on this thing before. This one will have some overlap, but it also have some different stuff. So let's get started. So the two things I'll be talking about is, one of them is online list labeling, and this is a problem that I'll define. The other one is this idea of history independence, and this is a property that an algorithm can have. So the goal of this talk is to kind of convince you that history independence is an interesting thing to study, both in terms of upper bounds and lower bounds. And moreover, history independence has some kind of unexpected uses. And I'm going to use this problem of online list labeling as a case study for showing how history independence can be useful. Okay. So first what I'm going to do is just define the online list labeling problem. And then I'll say all the results for that problem, and then later we'll come back to this idea of history independence. So what is the online list labeling problem? This problem, our goal is to maintain n elements in sorted order in an array, where the array is of size linear in the number of elements. And what's happening here is this is dynamic, so an adversary is coming in and inserting this element and deleting some elements. And what we can do as the algorithm is we're allowed to move stuff around. So for instance, right now we're moving this L around as the algorithm, and our goal is to be able to move around as few things as possible per insertion deletion of the adversary. And remember, our goal is we have to keep everything in sorted order all the time. So sometimes we have to move stuff around. If the adversary inserts something between these two, we have to move to make space for it. Okay, so does the problem definition make sense? Cool. So just to be clear, I'm showing it as having a universe of the alphabet, but actually imagine it as an infinite universe. The adversary can insert between any two as many times as it wants to. Okay, so one way to think about this problem is if you wanted to explain it to a child, you might say, okay, imagine you're a librarian and you have to store a bunch of books on the shelf. And throughout the day, you're going to be inserting some books and removing some books. And you can imagine two different types of libraries that you could possibly work in. So one of them would be the library that has no gaps between any of the books. And so when I insert a book in here, I'm going to have to move almost every book to make room for my new book. But if I left a whole bunch of gaps, then I don't have to move stuff around. So that's motivation for why in this problem in your array, you might want to preemptively leave some gaps in order to not have to move so much stuff around. Good. So I'll just go really briefly through kind of some history on this problem. This is quite an old problem. It was originally introduced in 1981 by Itai, Konheim, and Roda. And it has kind of been rediscovered several different times independently in several different contexts through the 80s and 90s. Additionally, it has found a number of applications. So probably the most well-known application is cache-oblivious B-trees. And a result that I'll mention in this talk immediately implies an improved bounds for cache-oblivious B-trees. And then it also has had a number of applications in different areas where some of them are in theory and some of them are in databases and other areas of practice. Okay. So back to the problem itself. Now I'll tell you what is known about this problem. So in the original paper that studied this problem, they showed an upper bound of log squared n. So what this means is that after every insertion and deletion that the adversary is doing, there is an algorithm so that the amount of elements we're moving around each time is log squared n.
I'm with that.
Originally was amortized, and then it was improved to be worst case by Willard. On the other hand, there's a lower bound at log n. So this is by Bulinek, Kotsky, and Mike Sachs. And what this lower bound shows is log n. So we know the correct answer is somewhere between log n and log squared n, and the question is, can we close this gap? What is the correct answer? So what I want to do now is take a slight detour before saying more of the results and just kind of get our hands on the problem a little bit and ask, like, the first time you see this problem, like, what is maybe the most natural type of strategy you would consider doing? And then I'll tell you that there are some lower bounds against particular natural types of strategies. So one natural strategy you could think of would be when an interval becomes too dense, when an interval of the array becomes too dense with elements, let's just rebalance that interval by spreading out its elements. Okay, so this will show us the adversary is inserting something. Let's say this became too dense, and now we're saying, okay, let's spread everything out, and in particular, let's spread everything out evenly. Okay?
So,
yeah?
Does our mental picture right now determine, it's deterministic. I was about to ask if it's deterministic or randomized. So currently we're deterministic.
Yes.
Yeah, okay.
Yes. This.
Does the insertions know where we, like when you do the next insertion, does it know how you balance stuff? The upper bounds, or does it have to kind of be specified in advance that this is the sequence that I'm going to?
Right. So if we're deterministic, then we can say, okay, the adversary knows everything. For randomized, we're imagining that the adversary is oblivious and does not know where we're placing things in the array.
The upper bounds, are they deterministically randomized to log squared?
The lower bounds?
The upper bounds, the log squared upper bounds.
Oh, the upper bound is deterministic. So this natural strategy has these two properties. One of them is that it's deterministic, assuming that we choose when an interval becomes too dense deterministically. And the other one is that it has this property called smoothness, where a smooth algorithm is simply defined as one that says, okay, take an interval and spread everything evenly along this interval. We're never going to spread things unevenly. We're always going to do it evenly. And it turns out that these two properties, deterministic and smooth, we know the correct answer if you restrict to algorithms that have these properties. And in particular, the correct answer is log squared n. So that is to say, you can get lower bounds. So for deterministic, Bulinek, Kotsky, and Sachs showed that this log squared n algorithm is tight for deterministic algorithms. And furthermore, Dietz and Zhang showed that log squared n is tight for any smooth algorithm, even if it's randomized. Okay, so the real question that we're asking here when we're asking can we close the gap is, can we use randomization and uneven rebalancing in order to improve over log squared n? And different groups of researchers had different ideas about whether this should be possible. So at least one group has conjectured that log squared n should be tight for all types of algorithms. And it's kind of hard to imagine why uneven rebalancing would help us here. Like, if I'm doing uneven rebalancing on an array, that means I'm making some areas dense and some areas sparse. And if I'm doing that, then the adversary should say, okay, I'm just going to insert into the dense areas you created.
But you just said that he is
oblivious,
okay.
yes. So you're getting the point maybe that this intuition is incorrect. So actually you can improve over log squared n by using randomization and uneven rebalancing. So in particular, the main result of this paper is that you can get a log to the 3/2 n algorithm for this problem. And this is an expected cost per insertion or deletion. This is a workshop on lower bounds. I'll also be talking about some lower bound stuff in a bit. Okay, so just to put this in the picture with everything else, our result shows that, okay, there was an upper bound of log squared n, there was a lower bound of log n. Now this upper bound is improved to log to the 3/2 n. And in particular, you'll recall that by necessity, this algorithm has to be both randomized and non-smooth, so do uneven rebalancing. Good. So I now just want to make a couple of observations about this result that I think are interesting. One of them is that it turns out that randomization and uneven rebalancing only help when your array is of a particular size. So if your array is linear size in the number of elements that are in the array, then randomization and uneven rebalancing do help. On the other hand, it was previously known that when your array is much bigger, is polynomial in the size of the number of elements, then we know that randomization and uneven rebalancing do not help, and there's a deterministic and smooth algorithm that gets the tight correct answer, which turns out to be log n. Okay. The second observation I want to make about this is that you might think, looking at this number log to the 3/2 n, it's maybe kind of unusual, and that you might think that if we can improve over log squared n, then we can probably get it all the way down to log n, maybe. But there's at least some evidence to suggest that maybe log to the 3/2 n could be the correct answer. And this comes in the form of saying, it turns out that log to the 3/2 n is tight for a particular natural class of algorithms. And this brings us back to the second topic of this talk, which is history independence. So it turns out that log to the 3/2 n is tight for the class of history independent algorithms. And I'll define what history independence is next. Okay, so now I'm going to transition from the list labeling problem to talking more about history independence. So are there any questions about list labeling stuff?
And for adaptive adversaries, is there a higher lower bound than log n?
No. There are no higher lower bounds than log n. Yeah, good question.
What's the idea for the log n lower bound?
Right. So
Like intuitively, why?
yeah.
Okay.
So I guess it's not simple. Maybe Mike Sachs has a better intuition than me, but like roughly speaking, it says, okay, it's always going to, like, the adversary can do insertions in such a way that if I look at this interval, it's pretty dense, and then if I look at a subinterval, that's also pretty dense, and if I look then I can always find these like nested intervals that are denser and denser and denser. And if my insertion strategy is to like always insert out this very dense part that I found, then that turns out to be like log n. Yeah, good question. Okay, so now on to this idea of history independence. So for this talk and this paper, the definition of history independence that we have is that the distribution over occupied slots in the array depends only on the number of elements that are currently present. Okay, so what does this mean? So first of all, what is this distribution that I'm talking about? Well, I'm talking about randomized algorithms. So for any randomized algorithm, we have, at any step, after any insertion and deletion, we have a distribution over which slots in the array are full. That's the distribution that I'm talking about. So it's the distribution over the randomness in the randomized algorithm. And what I'm saying here is that it depends only on the number of elements present. So if you tell me that there are 10 elements in the data structure, then I can exactly tell you what is the distribution over the occupied slots in the data structure.
Not even on the identity of those elements.
Yes, good question. Not on the identity of the elements. So this picture kind of shows like two arrays that both have 9 elements in them. The elements are different, and they both have the same slots that are occupied. In reality, it doesn't have to be the exact same slots, it's just the distribution is the same. Good. So in particular, the slots that are occupied do not depend on the history. So it does not depend on whatever the adversary did in the past, whatever insertions, deletions happens. That's completely independent of what is the current state of the data structure. Okay, so if you're satisfied with this definition of history independence, then you can ignore the following caveat, which I'll say for people who have studied history independence before. So the usual definition of history independence is that it actually depends, is that the state of the data structure depends only on the elements that are currently present in the data structure, as you've all said. Here, that's a little bit different, because I'm saying it only depends on the number of elements, whereas the usual definition is that it depends on only the elements that are currently present and not the past. It turns out that for the list labeling problem, it makes sense to define it in this way, because actually for the technical definition of the list labeling problem, these elements don't actually have values. I'm just showing it like this because it's kind of easier to see. In fact, in the list labeling problem, you just say, okay, I would like to insert an element like after the 5th element that's currently present. So there's not really an idea of values. Okay, so that's end of caveat.
So your log to the 3 halves algorithm, is it history independent?
It is. You're predicting the future, yes.
So, sorry, are we in the regime where you're doing length insertions and deletions?
Yes.
The lower bound has insertions, has deletions, or only insertions?
The lower bound?
Mike,
What's that again?
the log squared lower bound for deterministic has both insertions and deletions?
No, we only use
Insertions.
Yeah, my impression is that like the insertions only case is kind of viewed as capturing the complete hardness of this problem, and that deletions sort of come for free-ish. It's like not one of these problems where partially dynamic is way easier than fully dynamic.
So, I'm just trying to, my intuition is telling me, so if I insert a bunch of stuff, and then and then the deletions come at the high end or at the low end, let's say I get 5 deletions at the high end or 5 deletions. So I would expect the distributions would be different, that if they came at the high end, then things would tend to be distributed more towards the front, and if they came at the low end. But that's not true.
Well, it's not true for a history-independent algorithm. Like a history-independent algorithm is required to, if you insert a bunch of stuff at the beginning, it has to kind of spread it out.
But when you have only insertions, does it make sense to conjecture that history independence is without loss of generality, or that's not?
I mean, you can conjecture it. I don't know.
Because somehow there's no trace for the. Okay. Do you have an example of a non-history independent algorithm, not necessarily for list labeling?
Sure. With trees, or you keep an ordered list by trees. By rebalancing the tree, and when you insert things in different orders, the rebalancings are not necessarily the
I
same.
see the order method. Yeah, I see.
Okay, so our result in the context of history independence is that you can get a history independent upper and lower bounds of log to the 3/2 n. So what this means is that the history independent the upper bound does have the property of being history independent, and furthermore there's a lower bound for the class of history independent algorithms that is log to the 3/2 n. So we know that if you restrict your attention to only history independent algorithms, the correct answer is log to the 3/2 n. And the question now becomes, is a history independent algorithm the best thing that you can do? Or can you get better than log to the 3/2 n by getting rid of the property of history independence?
The lower bound uses both insertions and deletions, or is it again only for
it uses
insertions?
both. So history independence has been studied before in the context of this problem. And in particular, it was previously known that you can get a log squared n history independent algorithm. And so what this is saying is, okay, there was a log squared n algorithm to begin with. And this work is saying, by the way, we can match the state of the art at log squared n and also have this additional property on top of it that the algorithm is history independent. So they're getting history independence as like an additional nice property in its own right. Okay, so one more thing about history independence. You'll recall that any algorithm that beats log to the log squared n is by necessity both randomized and has uneven rebalancing. And if you think about it for a bit, you'll realize that history independence itself is kind of fundamentally at odds with being deterministic and smooth. And so my point is that you might ask the question of where in your algorithm does randomization and uneven rebalancing come into play? And the answer is in the form of history independence, because you can't really, like if you think about it, you can't really have a history independent algorithm that's fast and also is deterministic. Like this would be saying like, okay, I have 10 elements in my array and I'm deterministic, which means that I have to be filling exactly these very particular slots. And so if I insert an element, I might have to like shift everything over, if that makes sense.
Can you say about the smoothness also?
Yeah, the smoothness is maybe a bit less immediate than the deterministic, but the smoothness, you can think about it as like, if you see places in the array that have been, like, if you're doing these smooth rebalances where everything is spread out evenly, then you can kind of maybe look at the state of the array and notice where you've done the rebalances in the past based on which parts are actually smoothly spread out, and that this would tell you something about what happened in the past, roughly speaking.
So is this an intuition for a formal proof, or?
There exists no formally written proof down of this statement. Yes. Good. Okay. Okay, so just taking a step back for history independence in general, it has been kind of a widely studied thing. So it has been studied in a lot of basic data structures such as hash tables, heaps, and B trees, where the goal of this line of research has historically been to say, okay, we have this algorithm for a hash table or whatever. Now, can we get the additional property of history independence while matching the state-of-the-art bounds for this data structure? And that brings me to kind of the key point, I think, in this whole talk that I want to try to get across, which is the following. So history independence previously was viewed as a desirable property to achieve in its own right. For example, for security guarantees. So you can imagine that this could be useful in security because if an adversary looks at the state of your data structure, they don't gain any information about anything that happened in the past, and maybe that's information that you would like to hide. So that's the type of security that I'm talking about. But on the other hand, like in this work, we're using history independence in order to get a faster algorithm. So it turns out that history independence is useful not only for security guarantees, but it can also be used in order to actually get a faster algorithm. Okay, so now I'll just say what are the two things that I'm going to focus on for the rest of the time. So the first thing is I want to try to give you some intuition for like why history independence is actually useful for getting a faster algorithm. And I hope that this will also motivate why it might be interesting to study history independence from a lower bounds perspective, because we're saying, okay, history independence is a useful tool in algorithms, so we might wonder, okay, what are the limits of history independent algorithms, and therefore can we prove lower bounds on the family of history independent algorithms? And the second thing I want to show you is briefly like how does our history independent lower bound work, and in particular like how can one exploit the property of history independence in order to get a lower bound. And I would say the message of this part is kind of like, in general, there are a lot of data structures problems that we might be stuck on in terms of lower bounds, because lower bounds are hard to prove, and so sometimes we like to make additional assumptions in order to actually be able to get traction and prove something, and that one thing you could possibly assume as an additional assumption is my algorithm is history independent, and that's what the form of this lower bound is. Okay, so on to number 1. Why is history independence useful in an upper bound? And here's the short answer. So the short answer is that history independence is all about hiding information from an adversary. Okay, so in particular, for the purposes of security, which is how they used history independence in prior work, what we're saying is that by observing the state of the data structure, an adversary cannot gain any information about the history of insertions and deletions. Okay, so then on the other hand, if you want to use history independence for speed, like we do in this work, we're saying essentially the opposite. So we're saying by knowing the history of insertions and deletions, the adversary cannot determine the current state of the data structure. Okay, so these are the same statements and they're just flipped. And the reason that these statements are both true is by the definition of history independence, where we're saying, okay, the current state of the data structure is completely independent of the past. And so if I know one, I know no information about the other, and vice versa. So this is the intuition about why history independence should be helpful in upper bounds. I want to get a little bit more concrete about this and go into the list labeling problem and say, like, how does history independence help us there? Nothing that I'll say in this talk will be very technical in the details. Most of it will be more high-level conceptual, but I do have like extra slides on details, so if anyone is interested in talking throughout this week, we can do that. Okay, so for the upper bound for list labeling, recall that the algorithm has expected cost log to the 3/2 n. That's just the result that we're trying to prove here. And what history independence gives us is that it allows us to be able to state a weaker goal. And the weaker goal is of the following form. So the weaker goal says, we would like an algorithm so that if you tell me that the next insertion is going to be completely uniformly random, then I get a fast algorithm at log to the 3/2 n. And this is a step that we have in the paper that and it has a black box around it because I want you to view it as a black box. And so I will not say any details about how you achieve this weaker goal, but we're going to say, okay, suppose you can achieve this weaker goal, then we would like to be able to put history independence on top of this black box to be able to achieve the final goal. Okay, so in this weaker goal, in particular, the algorithm that we have has the following guarantee. The vast majority of the array slots are fast to update. So if I have my array and the adversary does an insertion or deletion at one of many different points, it's going to be cheap. It's going to be log to the 3/2 n. However, there's a few spots in the array that are going to be slow. And by slow, I mean log squared n. So we're in this situation where we have most of the places you could insert will be fast, but there's going to be a couple that are going to be slow.
So what is the universe of, what's the universe of things that can be inserted?
It's anything. So the insertion could be, so like if I have a pair of elements in the array that are next to each other, I can insert over and over as many times as I want
Right,
in
so
between
I
them.
guess what I'm saying, when you say if the next insertion deletion is random, so that is,
Oh.
what do you mean
Oh,
by
good
random?
question. So by random, what I mean is that think of all of the elements that are currently in the array. I'm going to uniformly randomly pick a rank.
Right.
So
Okay, so
there's
you
n
pick one of the
elements. I'm
gaps.
picking an element.
Yeah.
I'm picking a number from 1 to n plus 1.
Got it.
Yeah, and inserting there. And actually, the distinction between picking a rank randomly and picking a spot in the array randomly is not a significant distinction if your algorithm has the property that things are relatively evenly spread out, because you'll recall that the number of elements in the array is linear in the size of the array. So if there's an element every constant number of slots in the array, then those two things are basically the same. Okay. So the first question is, why does achieving this weaker bound not just completely solve the problem in the first place? We have that most of the slots in the array are cheap to insert into. So why does that not just solve the problem in the first place? Well, it turns out we're still vulnerable to the adversary here. And the reason we're vulnerable to the adversary is, well, because we have these slow spots, and what if the adversary knows the slow spots? So if the adversary knows, okay, hey, this is a slow spot, they can just keep inserting there over and over again, and your cost is going to be log squared n. Who cares if the rest of the array has cheap, if the adversary knows where to insert to make the expensive one? Okay, so then our goal is going to be able to hide these expensive spots from the array, from the adversary. Okay, so we're in a situation where we have a problem where the adversary may know the dense regions of the array and therefore be able to exploit them. And on the other hand, and so this brings up the question, can we hide the dense regions of the array from the adversary? And the answer is yes, we can do that using the idea of history independence. And so you'll recall that the definition of history independence is that the distribution of occupied slots in the array depends only on the number of elements currently present. So what this means is that the following is not possible. The adversary can't say, hey, I'm going to come up with a really clever sequence of insertions and deletions to put the array in a really bad spot to make everything expensive. The adversary, by definition, cannot do that because the state of the current array is completely independent of what the adversary is even doing in the past. So the adversary in particular, like Mike said before, can't just insert all at one place and expect to create a dense region. So I'm hiding some details here from you. This is kind of an intuition for how history independence should help. There's a little bit more that goes into the idea. Yes?
Yeah, so I just wanted to ask a little more about this. So if I have a history independent distribution, so that when there are a certain number of elements, T elements, then there's a fixed distribution no matter what those T are. Right?
Yes.
Okay. But that distribution could still have dense spots that the adversary will know
Yes.
about. So how does history independence protect you from
Yes, that is a fantastic question that I was trying to hide. So you need one more ingredient here, which is what we call like the random shift. So if you imagine you take the array and you like create a larger dummy array and you put your array in kind of a random spot in the larger dummy array, then we can then if the algorithm creates dense spots, then the adversary won't know exactly where they are because we're taking the whole array and like shifting it.
But you cannot make a shift like too many times, right? Like it would cost way too much to move everything from here to here.
Yeah, good question. It's not a literal shift. It's like at the very beginning, we're just defining our whole array to be like at a random spot. By like inserting dummy elements, let's say. Okay, so the summary of this is that, roughly speaking, the final log to the 3/2 n algorithm is a combination of the algorithm that handles the case where you have a random next insertion, and that was the black box from before, and you take that and add to it the known log squared n history independent algorithm, and by combining those, you get, roughly speaking, the log to the 3/2 n algorithm.
So Nicole, just to understand, the first reduction has nothing to do with history independence. You're saying that if I come up with a data structure that handles random order, then I can use that. Is that what you're saying?
Yes.
Okay.
Yeah, good question. It's not a literal shift. It's like at the very beginning, we're just defining our whole array to be like at a random spot. By like inserting dummy elements, let's say.
then I handle like forget the second part. You're saying that you can reduce the problem to handling the random sequence?
That's a good question. So not in a black box way. So the way that this works is not a direct reduction to the black box algorithm. Instead, it is the case that it turns out that this algorithm and this algorithm have very similar structures, so like it's kind of natural to combine them.
Another quick question. The bottom algorithm is deterministic?
It's randomized.
And do you plan to tell us very quickly the 3/2, why 3/2? Or
Oh,
maybe
why
skip
3/2
that?
for, so I have some stuff about the lower bound, and there's something about why 3/2 for the lower bound. For the upper bound, it's a little bit difficult because I haven't gone into any details of what the upper bound is, but the 3/2, roughly speaking, comes from a random walk. So if I start at the origin and I do a random walk for t steps, then I'm probably going to end up about square root t from the origin, and that's where like the square root log n factor comes from.
So, but does that, so Bender et al. Had this history-independent log squared n, right?
Mm-hmm.
Is it just reanalyzing their data structure for random insertions, or it's more, or you're actually changing that?
We're changing the data structure.
Is the algorithm itself too complicated to show us the pseudocode, I guess?
No, it's not. Like I've given a talk on this before, and I had the algorithm, and I have it on extra slides at the end, but I thought that this is a lower bounds thing. I should maybe not do that.
I'd love to see it.
We're not that
Okay. Okay, how about I say something about the lower bound, and then if there's time, I'll come back, or afterwards, to the upper bound. Okay, so for the lower bound, the result is, again, that any history-independent algorithm has cost log to the 3/2 n at least. And the framework behind this is actually the same framework that the algorithms use. And it's the following. So we have the array down here, and then we break it up into nested intervals. So this interval is the whole array. This one is split into 2, then 4, then 8, etc. And what we're asking about here is, what is the difference in density between two adjacent intervals? So if I look at these two intervals that correspond to this part of the array and this part of the array, I can ask, how dense is this part of the array, how dense is this part of the array, and how much do those differ? And the way that the upper bounds roughly work is saying, okay, if I ever on any of these levels get too much of a density differential between two different intervals that are next to each other, I'm going to rebalance those intervals so that I don't have such a density differential. In the lower bound, we also consider density differentials between different intervals that are next to each other. And we use the following fact, which is not immediate and takes some time to prove, but I'm just going to say the fact. And the fact is that for any array configuration, as in for any way that the data could be in the array, it turns out that the average density difference between adjacent intervals is about 1 over square root log n. And when I say average density difference, what I really mean is I'm taking a weighted average over all of these levels. So I'm taking the average density difference on this level plus the average density difference on this level plus all of them, and then I'm dividing it by the number of levels so that each level gives the same contribution. So that log squared n over there is where the log is, or sorry, that square root log n is where the square root log n comes from in the lower bound to get log to the 3/2 of n. Okay, so if you take this thing as a fact, then roughly speaking, the lower bound works as follows. we're saying, okay, let's pick a random spot in the array and let's insert here. And then let's delete from the end, delete the last element, and let's do those alternately. So I'm doing insert, delete, etc. And the point of doing this is so that we can use the property of history independence to say that, okay, if I do an insertion and then a deletion, I'm left with the same number of elements in the array that I started with. And because of that, I'm going to have the same distribution of slots filled after every insertion deletion pair. Okay, so I start out with some distribution of how the slots should be filled. I perform an insertion deletion pair and it stays the same by history independence. And then the idea is that because we chose the insertion position randomly, if we look at like some interval containing the insertion position and then we look at an adjacent interval, those things should roughly have about the average density difference between them just because we picked the spot randomly. And so we can say then that because the insertion position was chosen randomly, like both before and after the insertions and deletions, the density difference between these two intervals is roughly 1 over square root log n, which is the average that was computed before and that I did not show. And then the idea is to say that, okay, well, work is required to spread out the inserted elements in order to achieve this density difference. So what we're saying is, okay, if we insert here over and over again, then naturally this is going to become super dense. But because we know that the density difference between this and this is not too much, eventually we're going to have to like spread some stuff from here over to here so that the difference becomes only our like 1 over square root log n. Okay, so that's roughly speaking the idea of the lower bound.
Nicole, so is your distribution, when you say delete the last element, that's the last element of, like the largest element?
The largest element, yes.
And the distribution is that you pick a random permutation of like length 2n, and each time you delete the large, like, so this gives you a hard distribution over the inputs, no, that you fix. And what is that distribution?
Are you asking how this random?
No, I'm saying, is there some sort of like a Yaws minimax or something like that happening, that you have a hard input distribution for your input or not for the problem?
Well, I guess the input distribution is like you choose the insertion spot uniformly at random.
I guess I'm confused. The spot you're choosing is inside the array, or is it inside the input?
It's a random
Because you
rank,
don't know
right?
the array.
Yeah, let's say it's a random rank, as in there are n elements that are in the array and we're choosing a number between 1 and n plus 1 for where we're going to insert. Okay, so now let me just, much time? I'll just say some open problems for future work. So the question for list labeling is, what is the correct answer between log to the 3/2 n and log n? So there's two different options for what the answer could be. So for instance, we can say, can we get cost actually log n? In which case we'd have to give up history independence, and I guess intuition behind this would be, well, history independence might be an expensive thing to maintain, and so maybe you can get better if you get rid of the property of history independence. On the other hand, maybe there's a lower bound, a general lower bound of log to the 3/2 n, and maybe some intuition behind this option would be that, you know, giving up history independence kind of gives the adversary more power, so maybe it's not possible. As another more broad open problem, the question would be, you know, can this idea of history independence help for other problems? So like we used the idea of history independence to get a faster algorithm. Can it be used for other problems to also get a faster algorithm? And also, can we get some other lower bounds for problems that seem to be difficult to get general lower bounds? Can we get lower bounds for them specifically for history independent algorithms? Okay, So that's all. I could talk more. I don't know how much time there is. I can talk more about upper bounds like afterwards privately or
I'm
I don't
happy
know.
to hear 10 minutes on the upper bound.
Upper bound.
Yeah.
Okay.
Yeah.
Okay. Cool. So this will be like some random slides that aren't true. Well, some of this is true. Okay. So in order to understand the lower bound, we first need to understand what does the original lower bound do for this problem? What is the log squared n, upper bound? What is the original, like from 1981, what does this algorithm do? And then we'll think about how to modify it. So the way this works is we have these nested intervals from before. And what we're going to do is say, OK, the pivot of each, we're going to have an invariant. And the invariant is going to say the so-called pivot of each interval falls in the middle 1 over log n fraction of the elements. OK, what is the pivot? The pivot of an interval is simply the element that falls right in the middle of that interval. So if I'm looking at this interval, the pivot of this interval will be like the element that just happens to fall right in the middle. Okay, so this invariant that I'm having is the pivot of each interval falls within the middle 1 over log n fraction of the elements in that interval. That is to say, the element that actually appears in the middle is close to the median element. Okay, so what this means, so like if the pivot were actually not close to the median, like if the pivot of this whole entire thing, the element that was here was like really near to the beginning, then you'll notice that those two subintervals would be very unbalanced. One would be very dense, one would be very sparse. So this invariant is saying, okay, we can't have too much density differential between adjacent intervals.
So the intervals are of the array, not of the element.
Yes,
Oh,
good
okay.
good point. Yes, the intervals are literally these things that are
Right,
drawn.
the middle could be empty, right? So then you mean what, the closest thing to the middle?
Yeah, let's say off by 1. Yeah, sure. Okay, so now let's imagine that this is our array right now, and now we can verify that this is a valid array configuration based on the invariant. So what's going to happen is we say, okay, we look at what's written on the bottom, and we ask ourselves, what is the pivot? The pivot is j, because j appears right in the middle of the array, maybe off by 1. And then we ask ourselves, okay, does j fall in the middle 1 over log fraction of the actual elements themselves, which is this blue box? And the answer is yes, so that's good, that the invariant is satisfied, and we just keep going for all of the other intervals. We say, okay, this is the pivot, this is the valid candidate set where the pivot should fall, and then we keep going and check that that is satisfied for all of the intervals going all the way down to the bottom. Okay. So far what I've told you is just an invariant. I haven't said an algorithm. I haven't said like what happens when you violate this invariant. What do you do? So the answer is that when you violate the invariant, you do the following. So let's say we're trying to insert an item with the label P. Then what we're going to do is check, okay, is the pivot still valid from before? Now we're going to eventually get to a situation where the pivot is no longer valid. Okay, the pivot here is Q. Q falls right in the middle of the interval according to this, but it falls outside of the valid candidate set, and so this is no longer valid, and we just rebuild the whole thing. And when we rebuild the whole thing, what do we choose as our pivot? We just choose the median element deterministically. So this is a deterministic algorithm, and we're just saying, okay, rebuild this whole thing recursively, select the median as the pivot, and what this amounts to is basically we're taking this whole interval and spreading everything out evenly with some off by 1 errors. Okay, so that's how the classical solution works. And now we can ask the question of like, how can you improve this?
And the reason this is O of log squared n is because now you don't need to touch that space, and I can reconstruct it for like n over log n insertions.
Yes.
Okay.
So let me say the source of the two log factors to reiterate what you've all said. So one source of the log n factor is that there's log n levels. The other source of the log n factor is the cost of maintaining the invariant at each level. So each rebuild of an interval of size some s requires s over log n insertions deletions, because 1 over log n is our fraction that we need to keep the pivot into. And so our cost is then going to become log n. So now the idea that we can have is, okay, well, how about we just change the parameters of this algorithm? How about instead of doing 1 over log n, we have 1 over k for some k that's smaller than log n. And then if you do the calculations from the previous slide, it will come out to something better than log squared.
But you would hope for this improved invariant only for the random distribution, right?
Yes.
Why? I'm not following.
I think it might become clear. We can ask. Okay, so now the cost of maintaining this new invariant with the new parameter k is going to be, the final cost is going to be k log n. So if we can set k to be square root log n, then that would be great. The point of this is, well, it doesn't work. So if you actually do this and you say, okay, I'm going to allow these pivot candidate sets to be too big, and so therefore I have to rebalance less often. If I do that, then some intervals can actually overflow. So let me not go through some details here, but basically, if you assert that you're only going to rebalance when the pivot goes outside of this very large range, then you can calculate the densities at each level, and you can say, okay, the densities form a random walk. This is the random walk that I was talking about in response to your question, G. And this random walk tells us that actually when you get to the bottom and you consider one of these small intervals, it's going to overflow. However, it's not going to overflow too often because it's a random walk of densities. And so this is how you get that guarantee that I was mentioning before, where we have like, okay, for most places in the array, we're going to be good to insert into. But if you have this bad situation where you have the density is high in these like nested intervals, then you're in a bad situation and you're going to overflow. And the way that you deal with this overflowing is to just revert to the original algorithm. Okay. Okay, what is all this? Okay. Okay, solution to the overflow. Whenever an interval gets too dense, we're just going to revert back to the log squared n solution for that interval. So for that reason, we have an array, and most of the places are fast to insert into, and there's some slow ones, and that's kind of the place that we ended up before doing the whole history independent thing earlier on. Okay, I think I'm guessing that's everything I can say, and that should be the end. But I know that this algorithm is kind of presented in a weird order because we did the first thing and the last thing. So like I'll be happy to talk more about it for anyone who's interested. Okay, that's the end.
More questions to Nicole?
So the lower bound, it seems that it should work also when the elements just come from a uniform distribution over a segment. Is that true?
So what do you mean uniform over a segment?
So, think of real numbers and just pick 1 to guess you have to also delete one, but yeah, just pick a uniform element between 0 and
I
1,
see.
insert, and then delete whatever. Would the lower bound work for that? Or maybe
Oh.
delete
Oh, you're saying that if you insert at a random place and then delete, instead of deleting at the
like
end, you
your
delete at a random place?
adversary somehow keeps track of what elements are in the data, the data structure, right? Because it needs to pick a random. It needs to pick a random rank, and then like carefully select an element that has that rank to insert. My question is, with an adversary that is sort of indifferent to what's already inside, also work for the lower bound?
I see. So, right, so in the, like, I guess, technical definition of the list labeling problem, like, the values don't really exist. So once you pick the rank, like, that's the input to the thing. But then let's suppose we're in the version of the problem where you do have the values, and you're asking, would the history-independent lower bound still work if instead of picking a random rank, I, like, picked a random element out of some... My impression is that it probably would. It would probably approximate random rank well enough to go through. That's my guess.
Are there any notions of limited history independence that you're sort of exploring to try to get better upper bounds? I don't know what it would be defined to be, but I mean, instead of the entire distribution only depending on that number, if there's some, I don't know, moments of the distribution or properties that might be enough for the arguments to work?
Yeah, that's a good question, and no, I mean we haven't thought of any or haven't explored any like other notions of history independence to relax it, but that's a good question.
All right, let's thank Nicole again.